All right, so this, well, I was going to say this should be the last part, but I don't know. That might be a fourth part. Maybe the last part that you have to watch. We can clean up some of this stuff next week when we get back. Okay, so now we're going to be doing compositions of trig functions. I'm taking the sine of the inverse sine, and I'm taking the inverse cosine of the cosine. So what you're going to wish would happen is that these would just always undo each other and you just get this answer out. For example, when you take 2x and you divide by 2, you always get x out because these always cancel each other out. However, as we know, with some of these weird functions like squares and square roots, if you take the square root of -3 squared and then square root it, you don't get -3. When you square -3, you get 9. When you take the square root of 9, you get +3. So sometimes those things don't match up, like they don't undo each other like you wish they would. It's because of the nature of the square and the square root function, but that's the same is true because of the nature of the sine and the inverse sine function. Because we had to restrict it, and because we got domain and range and all these problems. Okay? So, I maybe should have done an extra sheet of notes in here to give you guys a little bit of a rundown, but well, let's just do these one at a time. Basically, if you take the sine of the inverse sine, ask yourself, what is this thing on the inside? That thing on the inside is a ratio. So when you take the inverse sine of a ratio, it's going to give you an angle. And then when you take the inverse sine of that angle, it's going to give you that ratio back. And it should always give you that ratio back. There should be no reason that it would give you any other ratio. So these are basically going to undo each other almost every time. So if you take the sine of the inverse sine of a ratio, they should undo each other and give you back your answer. However, there is one exception, and that would be this case here. If you take the inverse cosine of 3, well, the problem is that this is not a good ratio. The inverse sine and the inverse cosine have domains of -1 to 1. You can't have a sine ratio or a cosine ratio that is 3 over 1. Or in the unit circle, you can't have an x coordinate that is 3. It's out here, you know. So it's a bad ratio. So if these are bad ratios, then you have to say undefined. But as long as the ratio on the inside is a good ratio, then the sine is always going to undo the inverse sine. So the cosine of the inverse cosine of 0.9732 is 0.9732. As long as the ratio is good, they undo each other. If the ratio is not good, undefined. Now for the tangent, there's no such thing as a bad ratio. And I should be flipping back into the notes here. For the tangent, the domain is all reals. So every ratio is good. Why? Because on the unit circle, the tangent ratio ranges from 0 to 1 over root 3 to 1 to root 3 to 9 to 10, 11 to 12 to 1,000. The tangent ratio to infinity. Every ratio is accounted for, negative to positive. So for the tangent, this is the one function where this will always undo that, no matter what the ratio is. Okay? Think about what's on the inside. They're ratios. If they're good ratios, then they undo each other for the sine and cosine. If it's a tangent ratio, then it always undoes it. If it's a bad ratio for the sine and cosine, undefined. All right, so these are the ones that are a little more complex. Here, I'm taking the sine of an angle. When I take the sine of an angle, it gives me a ratio for an output. And when I take the inverse sine of that ratio, it's going to give me an angle answer. The problem is it always going to give me this angle answer? Well, the answer to that is going to be yes, as long as that angle is in the output range for the inverse sine function. Is pi 6 in the output range for that function? Yes, it is. So then it is going to give you pi 6. However, if you're taking the tangent of the sine of an angle that's outside that, it's not going to give you that one. It's going to give you a different one. So that's where the complexity comes in. Okay? So here's how I do these. I'll just start it from scratch. I still draw my circle. I do it kind of the same way as I always do. I find pi 6. Pi 6 is right here. And then I say whenever I take the sine of pi 6, it's going to give me this ratio, 1/2. I mean, you don't even care what the ratio is, but it would be 1/2. And then when you take the inverse sine of 1/2, it's going to give you an angle in these two quadrants. So yeah, it's going to give you that exact same angle. So it's pi 6. So yes, this one undid it. However, this angle, 7 pi 6, is not in the output range. So my answer is not going to be 7 pi 6. So this is why the next test is going to be difficult. If you're not thinking and you're not working with these, you're going to just put down 7 pi 6 and you're going to get it wrong. So where is 7 pi 6? 7 pi 6 is right there. The tangent ratio is, the sine ratio is, the y coordinate is 1/2. So where else is the sine of an angle equal to that 1/2? Well, that's also there and there. So those are the two spots. This is the one I'm taking the sine of, but when I take the arcsine, it's not going to give me that angle back out. It's going to give me the angle between here and here. So my answer is going to be pi 6. So this one undid this one did not. Cosine. 2 pi thirds is right here. Cosine is the x-coordinate, so these are the two angles that will have this ratio for the cosine. However, when I take the inverse cosine of that ratio, what angle is it going to give me? Well, it's going to give me the angle from 0 to 2 pi, so pi, excuse me. So yeah, it is going to give me this angle, this 2 pi thirds. Because this angle is in the output range of that inverse cosine, that's just going to undo it. But I draw the pictures for all of them. That's the way I roll. 7 pi fourths. 1, 2, 3, 4, 5, 6. So 7 pi fourths is down here. That's this one. We're taking the cosine of it, so it's going to give me an x-coordinate. Well, there's another spot up here where the cosine has that same x-coordinate, that same ratio. Now, when I take the arc cosine of that ratio, it is not going to give me this one. It's going to give me the one from 0 to 2 pi, to pi, sorry. So the answer is pi fourths. Do we really need to do all these? Yeah, I guess keep going. You can stop the video anytime you want, right? So negative pi thirds is the angle. So that's negative pi thirds. That's down here. The tangent. So where is the tangent ratio is going to be the same? If you remember the period of the tangent, they're always kind of across from each other. So this ratio, all students take calculus. So this is negative square root of 3. The other place where you have a negative square root of 3 is over here, right? So those are my two angles that have that ratio. When I take the inverse tangent of that ratio, which of those two angles am I going to want? I want the one that's down here, so negative pi thirds. That one's right. That one just undid it because the angle's in the right spot. Of course, that's not always going to happen. 5 pi 6, that's right here. 5 pi 6. It's going to give me a tangent ratio that is 1 over root 3, I think negative. The other place where you have a negative 1 over root 3 is right there. That is 11 pi 6. So those are my two angles that have that ratio. When you take the inverse tangent of that ratio, it's going to give you an angle from here to here. So if you're not careful, you're going to say, well, I want this one. It's in the right quadrant. And you're going to be wrong because you got eaten by the monster. Yeah, I want that angle, but I don't want the angle that goes through the third quadrant. I want the shortcut angle, negative pi 6. All right, so these are now no longer unit circle angles. In fact, These up here, you could have actually worked them from the inside out. You could have actually calculated this and then taken the inverse tangent of that like we did up here. But the way I did these actually kind of sets you up for making these ones here a lot easier. This is not a unit circle angle. That's all right, just find it. This would be 10 pi tenths, because it's pi. So 11 pi tenths would just kind of be right here. Again, it's not on my unit circle, but it's not a known angle on my unit circle, but it's an angle in the unit circle. And the reference angle there would be 1 pi tenth. Okay? So when I take the sine of that, it's going to give me this ratio. If I project that, then that's a y coordinate. If I project that y coordinate over here, there's going to be another angle that will have that exact same ratio. And that reference angle there is going to be pi tenths still. When I take the inverse sine, I want the angle that goes from here to here. So I want this angle right there, that little shortcut angle. That angle is negative pi tenths. Okay? Inverse cosine of the cosine. All right. Find the angle. Negative 2 pi 11ths. That's going to be down here somewhere. The reference angle is going to be 2 pi 11ths. When I take the cosine, it's going to give me an x-coordinate. That x-coordinate is going to project up to here for another angle that when you take the cosine of that angle, it'll also give you the same ratio. And because the inverse cosine will spit out an angle in these two quadrants, I want this angle. Reference angle is 2 pi 11ths, so my answer is 2 pi 11ths. All right, 12 minutes. We got 5 more to go. Yeah, I think I'm going to do one last bit. So that's that set of problems. Notice these are all inverse functions of each other. The next set, we start talking about functions that don't match up exactly. The tangent of the inverse sine, the sine of the inverse cosine. So these are going to be a little bit different. So I'm going to do one more video. You know, really, if you got through 3 videos, maybe we could do, I'm going to just keep going.